Hi everyone. My name is Jaewook Lee, or Jay. I'm from the Institute of Lightweight Design at TU Vienna. In this talk, I'd like to tell you about our recent work for modeling lubricated contact zones in orthogonal cutting. And we formulate this modeling as solving fluid structure contact interaction problem and come up with or develop a modular framework for that. This is close collaboration work with computational analysis group at RWTH Aachen, as well as the experimental teams at TU Dortmund. So orthogonal cutting. Orthogonal cutting itself is not commonly used for a production technique. Instead, it is a generalization technique that is used mostly in research for chip formation analysis. And here, as you see on the right-hand side, this provides idealized 2D abstraction for the machining process, where we can better isolate each influencing factors for the experiments. And the chip formation analysis is relevant in any kind of machining process. So for example, on the left-hand side, you see turning, and there are others like milling, drilling, grinding, and sawing. And all those processes create chips as a result of interactions between the tools and the workpiece. Especially for this work, we're interested in tribological interaction at the secondary shear zone. So if you see on the left-hand side, the white box here indicates secondary shear zone. And mainly tribological interactions take place here as tool and chip goes through tangential relative movements. So we want to learn more about the phenomena that take place here, and of course then create a model or numerical model which can reflect various factors that we're interested in, for example, geometry, temperature, pressure, and relative velocity to characterize friction behavior. And once we have that, we'd like to embed this in our multi-scale chip formulation analysis in order to improve the tool topography design to in-long tools lifespan, as well as products quality. So unless you've already worked in machining process, you probably don't have any reference points, just like I did at the beginning of this project. So I prepared or received 2 videos to clarify the motivation of this work. So on the left-hand side, you see an experiment without the lubrication, and the right-hand side, you see with the lubrication. And this is a high-speed camera recording. So now we see the lubricated cutting. So on the right-hand side, results in more homogeneous and thinner chip than the dry one on the left-hand side. And that is the goal. That is good, and we can have that as reference point. And of course, with that, we want to learn a little bit more about this. So moving forward, the focus on the framework we've been working on, starting with the overview. In order to incorporate the intermediate medium or the fluid in between, we need a fluid module. And we have a structure module for the chip and the workpiece. And these two, the interaction between these two structures are considered using contact. And the fluid structure interaction, FSI, and the title suggests, so we're interested in employing spline-based methods here. So as a starting point, we have an in-house finite element fluid solver called XNS, and we have some FSI features already prepared. And after that, we were looking for a library that supports IGA capabilities, and we came across MFEM and started using it. quick overview for two domains, so fluid and structure. In the fluid domain, we use incompressible Navier-Stokes with Newtonian fluid. Employ here a stabilized finite element formulation with linear elements. We have moving domains, and it is taken into consideration with ALE and space-time at OR, along with linear elastic mesh optic methods here. And our focus is on boundary conforming methods and supporting the spline-based boundary definitions. For structure dynamics, we have the equation of motion with IGA or NURBS discretization. And here, so the metal's behavior is modeled using J2 plasticity and Johnson-Cook-Harding law. Yeah, so utilizing these two individual solvers, one for fluid and one for structure, we couple them using partitioned approach. So for spatial coupling, we take advantage of the interface spline, which is identical for both sides. And one of the options here is finite interpolation elements. Here we have fluid's boundary nodes that sits on the spline. And using, for example, point inversion, we can determine its corresponding parametric coordinates on the spline. And using that fact, all we have to do is multiply its load or any data with the basis function. And due to partition of unity, during this process, we don't use any original quantities here. Second option is NURBS enhanced finite element method. Here, you give a special treatment to the boundary, or no, to the elements that's on the boundary, and to their bases that sits on the boundary. So here we take NURBS to describe them directly, and through a special mapping, you can directly integrate fluid loads on the control points, which eliminates any extra interpolation or projection steps here. For temporal coupling, we use Robin-Neumann scheme. We need this to properly incorporate the fluid pockets in our model, which may cause, which causes so-called incompressibility dilemma. And by using this Robin condition, we allow artificial flux during the coupling, and as the solution converges, this flux should vanish as well. And for the details, I've also left a paper here. I'll link to the paper. And at last, some relaxation and acceleration schemes in order to help the convergence. Yeah, so contact module. First, I'd like to highlight the nearest point search. And sadly, this wasn't as straightforward as I expected. So here we have square distance minimization problem. And we initially thought that with all this, just Newton iteration would magically just take care of everything. Yeah, unfortunately, that wasn't the case. So we use a group of algorithms. So we first start with Newton, and then SLSQP, so sequential quadratic programming, then Levenberg required to best make sure that search converges. And for initial guess, we build a KD tree using the sample physical points of the spline. Oh, yeah, and just for this workshop, I prepared a tiny test case to visualize this. So we've been told that all these fonts and computers are all defined with splines, and well, I can confirm that. And so now we have a geometry, and to test this, we sample some random points in space, and using this approach, it finds the nearest point. Okay. Moving to the contact itself. So we took mortar not to surface method. And this is quite similar to Gauss point to surface methods, but just the difference is that this formulation uses average normal gap, and the gap is defined on the control point level and as well as the pressure. So now the coupling. So we have fluid solver and structure solver, and these two are strongly coupled. You can start with either side. Well, we just start with a fluid solver. So fluid solver, we solve the fluid domain, integrate the fluid tractions on the interface, and transfer it to the structural solver. And from structure side, take it as a boundary condition and compute the displacement. And as I mentioned before, we have Robin condition. So here we take very practical strategy. So the displacement comes from the structure solver. And instead of computing the Cauchy tractions at the structural side, we pass the fluid traction back into the fluid solver here. And since the two domains will balance the stress anyways, this leads to same converged solution, but with much less work. Just a short note on driver. So to drive the whole process, we decided to use a Python language. And to start with, we start with a Fortran module as our fluid solver is in Fortran. So we create an interface, and in the header, we can match some symbols here. And yeah, we can write a Python wrapper using PyBind, which allows a direct access to any of the buffer through NumPy arrays. And using the buffer protocol, we avoid any unnecessary copies during this whole process. Okay. So structure solver with MFEM, yeah, it's more straightforward, I guess. Yeah, for this work, we use shared memory parallelization and other than usually extensions that's which is similar to example 10, I believe. We extended the ODE solver for coupling loops. Domain integrator needed an accumulation function for plasticity. And contact integrator needed a function to register the target surface, so the foreign object. And yeah, all these actions are again exposed to Python using PyBind. And at last, putting all this together, you can write a coupling loop quite simple. So the first block for the fluid, second block for the structure. And I guess the whole motivation behind this is to use some other packages to visualize at any moment and manipulate some arrays or information during the prototyping stage. Okay. Yeah. Here now we have an example with our first model. So we have a tool on top as a rigid body, and it's also fixed in space. And the workpiece at the bottom and the fluid in between. They are in micrometer range, and the geometries come from the measurement, measured surface topography. And yeah, for these points, we fit a spline through it, and we make an we extrude to create a volume. Oh, and the domains are periodic in X direction here. So yeah, workpiece, we initialize it with some temperature, initial temperature, and the gamma B here. The bottom boundary, we apply pressure. This geometry works in the y-axis, and the constant velocity, we apply it to x-axis. Yeah, some results with 675 degree relative velocity of 22.5 meters per minute and pressure of 1.18 gigapascal. So here at the top, you see the model without the fluid, and yeah, bottom with the fluid. And we see the main difference here is the force distribution. And with the fluid, There's no void, so we see rather homogeneous force distribution with some peak where the contact occurs. However, without the fluid, solids goes through more deformation due to the void and still rather concentrated force distribution with a higher magnitude of the force. Yeah, just one more. Same condition with a different initial temperature, so about 650 degrees cooler. Yeah, here we see the similar behavior in general, but the solids behaved a little stiffer due to cold temperature and resulting in higher concentration in force distribution, and the peaks of the force magnitude peaks in a higher value. So yeah, with our approach here with all these, the model is to conduct a large-scale computational study, and we will run like thousands of simulations with varying initial conditions and boundary conditions and its values. So for each run, I'll analyze some resulting force ratios along the y-axis and the x, and the goal is to derive some reliable friction coefficient that we can use in chip formation simulations. Yeah, so full details you can see in our paper and left the link on the bottom. Okay. Yeah, to wrap up, so we do have some plans for extending this model. So for example, some advanced mesh update methods like surface reconstruction virtual region method right here. So yeah, it manages large deformation and shifting and even splitting domains. But as you see, it just deactivates the corner elements once it splits. So we'll have to come with just elegant way to manage those. And yeah, regarding the contact, we're considering adhesion model, and the validation and scaling up. Of course, the problem size and to 3D is planned. So splines are cool, and if anyone's need a tool to prepare or process some splines, I'd like to introduce our package that we worked on, the Spline-Py. It's a Python package with some C++ backend. Comes with a lot of geometric features and visualization capabilities. And of course, one of the interesting feature might be the microstructures. Our colleague Jaewook implemented this Bezier composition for creating microstructures and the full demo. And it supports MFEM export, most importantly. Currently, I noticed that there was some issue with automatic node-to-edge conversion with an MFEM, but we have a solution for that, and I created a PR for it. Okay. That was it from my side. Thank you so much.
So just to clarify, with your sorry, I forgot the name, Spline-Py. With that package, you can generate MFEM NURBS meshes.
Yes.
Did I understand that correctly?
Yes, the single patch is no problem. With the multi-patch, let's say it's not two edges creation.
Single patch,
but yeah, definitely.
With those primitives, that's one of the things that people have been asking us, how to generate NURBS meshes. So that's pretty cool. Okay, I'll take the microphone. There are questions from the audience.
Hi, Jaewook. I have a conceptual question. So you have lubrication and you don't.
Mm-hmm.
And with lubrication, the pressure is reduced. And I'm wondering about the temperature. The first test you had very high temperature, and the second you had, it looks like room temperature. Is that coming from friction in the simulation, or
this given as a initial condition, but it comes from the actual operation, and the heat generation usually comes from the plastic deformation at the primary zone, which I can also show here. Mouse here. Yeah. So around this part, they call it the primary zone, and through the plastic deformation, it creates a lot of heat. And my experimental partners at the team have told me 600 is already too low for actual operation.
Thank you.
Yeah, that's the source. Yeah, okay.
Okay, other questions? I have one more for the structural MFEM-based part. Is this available somewhere in a PR or a branch?
Not yet, but it can be.
Cool. It
Yeah,
looked pretty
with
cool.
NURBS discretization. Yeah, that would be also cool.
Okay. There's no more questions. Let's thank Jaewook again.